In 3.7, we're going to look at maximizing or minimizing different situations, and this is referred to as optimization. So when we do various things, we want to optimize the supplies that we have. Think about using natural resources. We want to make the best use out of the natural resources that we have available. So an example that we do in pre-calculus has to do with building a pasture. And we can actually solve this one because it turns out to be a quadratic function. But let's suppose we have a pasture and we have, let's say we have 200 feet of fence to use. So the perimeter is where we put fence. So we have 200 feet of fence available to use. And we want to make this pasture as large as possible using that 200 feet of fence. So we're wanting to maximize our area. So that's our primary equation, the one that we're trying to maximize. So let's call the length x, the width y. So the area is x times y. And this is the equation we're trying to maximize. But we don't want two input variables in our function. So we need another equation to eliminate one of those variables. And that's going to be our secondary equation. Notice if this is x, this is also x. If this is y, this is y. And if we're going to make this as large as possible, we're going to use all of the fence that we have available. And we have 200 feet available. So when we take the two x sizes and the two y sizes and add those together, that's going to use the full 200 feet of fence. So that establishes a relationship between x and y, and we can use this to eliminate one of these variables. So let's solve this for y. So subtract 2x from both sides. And then if we divide both sides by 2, since we have two terms on the right, divide each of those by 2. So we get y is 100 minus x. So this just establishes a relationship between y and x. But the real benefit here is that in the primary equation, the one that we are trying to maximize, we can replace y with this expression, 100 minus x. So now, instead of the area function having x and y, length and width in it, if you tell me the length, based on the restrictions we have in the secondary equation, that will automatically produce y, the width, and then that product will give us the area. Now we could distribute that and call that x times 100 or 100x, x times minus x, so minus x squared. So that's going to be a function of x. X is our input variable, and what we get when we plug x in is area. If we were to graph this, x would be our horizontal variable, and A, which stands for area, would be our vertical. So we're looking for this function, what is the most area we can produce? And in Math 112, we recognize that that's a parabola. Since the leading coefficient is negative, our parabola does something like this. So indeed, it does have a maximum. The pre-calculus way of doing that was to find the vertex there, and the vertex is where that maximum occurs. But not every function is quadratic. As we've looked at throughout this chapter, we can find a maximum or minimum regardless if it's a quadratic, if it's a trig, any other polynomial rational function, we can find where the maximums and minimums occur. So once we have our function, let's find our maximum. So we need our critical point. How do we get critical points? We take the derivative. What is our derivative here? Our derivative is minus 2x plus 100. How do we get critical points? We set our derivative equal to 0. If we add 2x to both sides, we get 100 is 2x. If we divide both sides by 2, we get that x equals 50 is our critical point. Now that doesn't guarantee that when x equals 50 that we have a maximum. It could be that that's a minimum. Knowing that we have a parabola that's upside down, we do know that that is going to be where the maximum occurs. But suppose we overlook the fact of what the shape is and we didn't have a graph. How could we make sure that when x is 50, that's a maximum and not a minimum? We could do either our first or our second derivative test. Remember, the first derivative test tests each side of our critical point to see if we go from increasing to decreasing or decreasing to increasing, and that tells us whether it's a max or a min. Or we could do the second derivative test. Well, to do that, we need the second derivative. So if this is our function, I'm sorry, our first derivative, our second derivative is -2. Notice there's no input in our second derivative. That means our second derivative is always negative. It's always concave down. The second derivative test says at a critical point, if we are concave down, then that critical point is a maximum. And indeed, if we substitute 50 into our second derivative, we get -2 because our second derivative is a constant. We are concave down at a critical point, so yes, 50 is a maximum. To find the corresponding area that goes with x being 50, we could substitute 50 into our area function. So the area when x is 50 is minus 50 squared plus 100 times 50. This is going to be -2500 plus 5000, which is +2500. So if the length is 50 feet, then the corresponding area, that is the largest area we can produce, is 2500 square feet. So that's the length, and that's the corresponding area. If we look back to our picture, this is maximized when x is 50 feet. If we want to get y, then we can come down to the equation here. Well, when x is 50, y is 100 minus 50, so that would make y 50 feet. And as we've already determined, the area when x is 50 is 2,500 square feet. Notice 50 feet times 50 feet would be 2,500 square feet. So that is the largest area we can produce using that amount of fence. We can make lots of other rectangles with that fence, but one that's 50 by 50 is going to be the largest that we can enclose. Now, a question from homework that we have is this one. If we have this function, y equals x squared, so let's just sketch that real quickly. That's a parabola, just your basic parabola. Find the points on the graph of the function that are closest to the point 0, 6. So 0, 6 is here. Oops. So we need to find what point is closest to that. Or in this case, it's going to be points, 2 points, because there will be a point on the left side that is equally as close as the point on the right side that is at the minimum distance. So what is it saying? If we compare the distance from here to here, here to here, here to each point on that parabola, which point on that parabola is going to be closest to that point 0, 6? So let's say our point is here. And let's sketch a little triangle here. This distance here, we're looking for that point which has an x value and a y value. The x value here is just whatever x is. The y value here is whatever we get when we plug that x value into x squared. So let's suppose, we don't know yet, but let's suppose that this x value is 2. Well, how do I get the corresponding y value? I plug it into my function. So if x is 2 here, then y would be 2 squared, or 4. If x here is 3, then y would be 3 squared, which is 9. So we are trying to minimize this distance. I'm going to call this distance d. And that's why I drew this triangle, because we can establish a relationship here between this side, this, and that hypotenuse, and then we can minimize d. The question is, how do we get this distance here? If this distance is x, how do we get this distance? Well, from here all the way to here is 6. This distance here is 6. From here to here, this distance, let's do that in blue. Notice that's the same as the given y value. If my point that I am closest to 0, 6 is here, this y value and that are going to have the same y value. So if I know, let's pull this pen out. If I know this full distance and I take away this part, then I would be left with this part up here. So we could write this distance, this side of the triangle, as an expression that full distance 6 minus that distance, which is whatever y is. So this distance is whatever the x coordinate is at this point. This height is the y coordinate. This total distance is 6, so this distance in here is the total distance, take away this part, so 6 minus y. So we can use the Pythagorean theorem to write an equation based on this triangle. So x squared plus the other side squared equals the hypotenuse squared. Or if we take the square root of both sides, then we get d is plus or minus the square root of x squared plus 6 minus y squared. Now, we don't want to have x and y as inputs on the right side of the equation. So how can we get rid of one of those? Think of f of x as being the same thing as y. So the y coordinate at this point is equal to the x coordinate squared. That's what the formula is for our parabola. So we're going to replace y with something that's equivalent to y at that point, which is x squared. So d is the square root of x squared plus 6 minus, in place of y, we're going to put x squared, and then that's all squared. Now we could leave it like that, or we can simplify what's under the radical. Let's square that parenthesis. So we have an x squared out front. If we square that parenthesis, we get 6 squared. We get this product twice, so minus x squared twice, so that'll be minus 12x squared. And then this part squared, so x squared squared, that's going to be x to the 4th. So we can combine some like terms. So we have an x to the 4th under the radical. We have 1 minus 12, so minus 11 x squared. And then we have a plus 36. So if you pick any given x value and plug in here, the answer to that is going to be the distance that that point is from 0, 6. That point is from 0, 6. So for example, if we pick this point, the x value here is 0. The y value is also 0. If I put a 0 in here, I get 0 minus 0 plus 36. So I get the square root of 36 is the distance, which is 6. Isn't the distance from here up to that point 6? And yes, it is. If this point is at 0, 6, then from here to here, that distance, that total distance is 6. And that's going to be true for any point. The distance from here to that point will be given by this formula. And like we said, technically it's plus and minus because there's going to be one on the right and one on the left. So how do we find the minimum? How do we find the closest point? We're looking for the minimum distance. So we want the distance minimized. How do we get the minimum value of any function? We take the derivative, we find the critical points, and we find at which critical point do we have a minimum value. So let's rewrite this radical. Instead of calling it the square root, let's call it that radical to the 1/2 power. And then take the derivative. So the derivative of this, we're going to have to use the chain rule. The outside function is a power, so we bring our power down. We do it to the 1 less power. We leave the function on the inside. And then we take the derivative of the inside and put it out here. So the derivative of the inside is 4x cubed. The derivative of the next term is minus 22x. And the derivative of a constant is 0. So with a negative exponent, this goes to the denominator. We have a 2 on bottom also. So on bottom, we have a 2. We're going to have this parenthesis to the positive 1/2 on bottom, or we could call that the square root on bottom. This doesn't have a negative exponent, so it stays on top. So that's our first derivative. So where do maximums or minimums occur? They occur at critical points, which is where our first derivative is either undefined or where our first derivative is equal to 0. So let's find out where our first derivative is 0. If we have a fraction equal to 0, the only way that can be true is if the numerator equals 0. We can factor out an x on the left side. If we factor out an x, we're left with a 4x squared and a 22. We could technically factor a 2 out of that parenthesis, but that's not going to get us a long way. So if we set each factor equal to 0, we get x equals 0, and we get 4x squared minus 22 equals 0. So this is a critical point, and then if we solve this for x, add 22 and divide by 4. So x squared is 22 divided by 4, or that's 11 over 2. Take the square root of both sides. So we get x is plus or minus. The square root of 4 on bottom is 2. The square root of 22 does not simplify. So these are our critical points. These are where our first derivative equals 0. So we just need to find out, okay, if these are our critical points, which of these are maximums, which of these are minimums? Or is one of them going to give us a minimum? We could get a second derivative and use the second derivative test, but if we look at our derivative, our first derivative is pretty messy. So instead of taking a second derivative and using the second derivative test, let's just utilize our first derivative to determine where we have a max and where we have a min. So let's group that together, and then we can copy that. So here is our first derivative. So if we look at our number line, thinking back to our parabola, our parabola goes from negative infinity to positive infinity. So on our number line, we could go from negative infinity to positive infinity. Now we have critical points of 0. We have plus the square root of 2 over 11, so that's over here. Or I said the square root of 2 over 11. The square root of 22 over 2, thinking ahead of myself. And negative the square root of 22 over 2. Now, in order to pick values to plug in to our first derivative, it would be nice if we had that as a decimal. So if I take the square root of 22 and divide that by 2, I get about 2.3, roughly 2.3. So that lets me know what kind of values I can plug in. So negative 3 would be here, a negative 1 would be here, 1 and 3. So I can plug those numbers into my first derivative to find out if I'm increasing or decreasing the interval. Notice that the denominator, I have a positive 2 times the square root. If we are using the square root notation, that indicates a positive value. We only include plus or minus when we take the square root of both sides. So this is positive, that's positive, so the denominator is positive. So it doesn't matter what number we get on bottom. If we end up with a positive sign on top, then we would have a positive over positive. If we end up with a negative sign on top, then we would have a negative over positive. So if we substitute in a negative 3, then I'm just going to do this real quickly in the calculator. We would have negative 3 cubed. So negative 3 to the third power, that's negative 27 times 4. And then we're going to subtract the result of doing 22 times negative 3. And for that, we get a negative. So negative over positive. In this interval, our first derivative is negative, so we are decreasing here. If we test the next interval by substituting in a negative 1, we still have a positive on bottom, but on top we have negative 1 cubed, so negative 1 to the third times 4, and then we're going to subtract 22 times negative 1, and that makes a positive. Positive over positive, that's positive, so we're increasing here. So at this number, we went from decreasing to increasing. So this point is a minimum. So this is one of our points that's a minimum. Now let's test 1 and 3. If we put a 1 in, then we're going to end up with 4 minus 22. So we're going to end up with a negative on top. So negative over positive is negative. So we're decreasing. And then if we put a 3 in, let's see. If we put a positive 3 in, we would have 3 to the third times 4 minus 22 times 3, so minus 66. And that's going to be positive on top. So we're back to increasing. So at this point, we also went from decreasing to increasing. So we have a minimum there. So we have a minimum what? A minimum distance. Why a minimum distance? Because our function represents distance. This is the picture of what we are minimizing. If we graph this function, our horizontal value, our x value, tells us where this point is located. Our vertical position, close that. Our vertical location tells us how far this point is from there. So we're looking, when is the distance as small as possible? So we minimize this function, and we found out that the distance is as small as possible when x is the square root of 22 over 3 and when x is negative, the square root of 22 over 3. That's where our minimums occur. Now to get the whole point, then we need to get the corresponding y value. Well, how do we do that? Remember that our point is on a parabola. Y equals x squared. So if we know the x point, if we know the x coordinate on the point that is closest to 0, 6, then we can find the y by plugging this into x. So our y value is the square root of 22 over 3 all squared. So square the top, square the bottom. Same thing over here. The y value is negative root 22 over 3 all squared. So negative root 22, negative times negative is positive, square root squared over 3 squared. So these are the 2 points that are the closest to the point at the top. They're the closest to this point here. So here, this is root 22 over 3, and the height is 22 over 9, and there's an equally close point on the other side. So that's what we're looking for here. That did not tell us how close we were. If we needed to know what the distance is, then we could substitute square root of 22 over 3 into this function that tells us what our distance is. All right, so let's take a look at this next one. So a rectangle is bounded by the x and y axes and the graph of this function. So what does the graph of this function look like? If we solve this, or if we divide each of those terms by 2, 6 over 2 is 3, x over 2 is x over 2, or 1/2 x. So that's just a straight line for the y-intercept of 3. Draw this. We have a y-intercept of 3, up 1, 2, 3, and a slope of negative 1/2. So go down 1 over 2, down 1 over 2. So we just have a line like this, where the equation of this line is y equals, we can call it either way, 3 minus 1/2 x, or 6 minus x over 2, or we could even call it 1/2 times 6 minus x. It doesn't matter. So our rectangle is bounded by the x-axis, the y-axis, and then that line. So our rectangle looks like this. So we want to find out what would the dimensions be of this rectangle such that we made the largest rectangle possible. So notice there are lots of rectangles we could make. We could make one that's really wide, but it's not very tall. We can make one that's less wide and that's taller. We can make one that's not very wide, but is very tall, and all of these are touching that line at the top. So notice this rectangle that I'm drawing now is bounded on the left and on the bottom by the axes, and then it's bounded by this line. So we're looking for which one of these rectangles is the largest. And when we say the largest, we mean has the most area. So what are the dimensions of the rectangle going to be? Let me get rid of these pieces. So the horizontal distance is x. This vertical distance is y. If we look at this ordered pair is x and y. The area of this triangle would be given by the x times y. Measured from the y-axis over to here, that's the x amount. Measured from the x-axis up to here, that's the y amount. Notice there are 2 different variables in this equation. We can't have 2 different variables, so we need to get rid of one. But notice at that point is on this line, and on this line, the y value is 1/2 6 minus x. In other words, on this line, the y value and this are the same. So we can replace y with any version of what we have y equal to. I'm just going to replace it with this version, I guess. Again, it doesn't matter. I'm going to replace y with 3 minus 1/2 x. So if we get rid of the parentheses, we get a is x times 3, so 3x, x times the next term, so 1/2 x squared. So area is a function of x. If you tell me x, if you tell me the x coordinate of that point, I don't even have to find out the y coordinate. I can plug that x in, and the answer is the area. So we want to find out what is the maximum area. So we want to maximize this function. So our primary equation describes our relationship. What is it that we are trying to maximize or minimize? We're trying to maximize area. So we have some function that you tell me x, and I'll tell you the maximum of that function. So to get that maximum, we need our critical points. How do we get critical points? We take the derivative of our function, which is 3 minus 1/2 times 2x. Bring the 2 down. We already have the 1/2 out front. 1/2 times 2 are going to cancel. So our first derivative is 3 minus x. Our critical points occur when our first derivative is 0. So we get x is 3. So our only critical point that we have is when x is 3. So hopefully that's going to be a maximum and not a minimum. So how do we verify that? We verify that either using the first derivative or the second derivative test. So let's take the second derivative. If this is our first derivative, our second derivative is minus 1. So if we substitute our critical point into our first derivative is, well, it's -1 because our second derivative is a constant. So at the critical point, remember what critical points are. That's where our slope is 0. We have a slope of 0 here. We are concave down. Our concavity at that point, we're concave down. So if we have a critical point and we're concave down, then yes, that point is going to be a maximum. For this function, of our input is x, our output is a, which stands for the area. So 3, that tells us the x coordinate required to get our maximum area. We could find out that maximum area if we need to by substituting a 3 into that function. Our area when x is 3 is 3 times 3 minus 3 squared, that's 9 times 1/2, or 9 over 2. 9 is 18 over 2 minus 9 over 2. So our maximum area is 9/2. Our maximum area is 9/2. If we need to know what our dimensions are, we need this distance, this horizontal distance to be 3. And then to get this vertical distance, we substitute 3, our x value, in to this equation to find out the y value at this point. So if we plug a 3 in, 6 minus 3 is 3. 3 times 1/2 is 3/2. So this distance is 3/2. Notice if we do this length times that width, 3 times 3/2 would indeed be 9/2. So that's the largest area that we can get under this restrictions, that we're bounded by the y-axis, the x-axis, and then it comes over and touches that line. So this line helps give us this function, and then we minimized that function. We found out for that function, where do we have a minimum value? Minimums occur at critical points, And we can't just assume when we get only one critical point that it is indeed, we're actually looking for a maximum this time, not a minimum. We can't just assume that because we only have one critical point that it is a maximum. What if we wrote our function wrong? So we verified that this critical point is indeed a maximum using the second derivative test. All right. So let's do one more. Let me get the picture of this one. They give us, we have uh, like a log, and then we're going to cut a wooden beam out of that log. And we want to cut the largest beam we can, or the strongest beam we can. So they tell us that the strength, it equals K times H squared over W, where this distance is H, and this distance is W. And notice that the distance from here to here, that's the diameter. That's the diameter. And we're told that distance is 16 inches. That's how big around the log is. So let's think about this. Let's draw a couple scenarios. So when we go to make our beam, we can make our beam not very tall, but we can make it really wide. We can make it really tall, but not very wide. If I make it thicker than that, then I'm going to have to sacrifice height. I can make it really wide to the point where it's going to have almost no thickness at all, but there's got to be a maximum point in there somewhere. If it's not very wide, then it's not going to be very stable. If it's not very tall and we're putting a load on it from the top, pushing down this way, if it's very thin, then it's not going to be very strong. So they give us that this equation right here relates the strength to height and width, where K is just some proportionality constant. So let's get rid of that. So what we're wanting to maximize, we're wanting to maximize S. We're wanting it as strong as possible. We're looking for the strongest beam. K H squared W. Now K is just some constant, and we don't know what that constant is. But H and W, those are both variables. So we actually want to get rid of one of those. We could get rid of both of them, or I'm sorry, we can't get rid of both of them, but we need to get rid of at least we need to get rid of one of them, so we have one input variable to our function. So we need an equation that relates H and W so that we can replace one of them. So if we look at our triangles, we have a right triangle here where this is the diameter, this is the height, and this is the width. So if we take the height squared plus the width squared, this squared plus that squared, that equals the diameter squared, which the diameter is 16. So this distance squared plus this distance squared equals 16 squared. So let's do this. Since this is H squared here, let's just solve this for H squared. So if we subtract W squared from both sides, we get the H squared is 16 squared. 16 squared, that's 256 minus W squared. So this is our secondary equation. Technically, we could take the square root of both sides, or we can just replace H squared with that quantity. So the strength is K times 256 minus W squared times W. Replace H squared with that, and we get this. So the strength is K times, let's multiply these two together, so that's 256 times W minus W squared times W. Again, keeping in mind that K is a constant. So this equation relates, if we were to know W, we could plug that in, and we would also technically need to know the proportionality. Then we could get the strength. So if we graph this, if we knew K, W would be our independent, strength would be our dependent. So we're looking for what is going to give us the maximum strength possible. Where is our largest strength factor going to be? So how do we maximize any function? We get the critical points. So we take the derivative. Again, K is a constant, so leave it alone. And then when we take the derivative of our parentheses, we get 256 minus 3W squared. If we set that equal to 0, well, K is not going to be 0. So what makes 256 minus 3W squared equal to 0? So add 3 to both sides. Add 3W squared to both sides. Divide both sides by 3. So W squared is 256 over 3. If we take the square root of both sides, then W is plus or minus. Well, W can't be negative. We don't want a negative width. So the square root of 256 is 16, and then 3 is not a perfect square. So this is our critical point. We want to verify that that critical point is indeed a maximum. So if we look at a number line, the smallest width we could have is 0, which technically we can't have a width of 0 or we're not going to have a board. The largest width we could have, I guess technically, is 16. But if we have a width of 16, we're not going to have any height. So we want to find out, is 16 roots of 3, is that really going to be a maximum? So we need to test a point in each interval to see, are we increasing and then decreasing? Or we could use our second derivative to find out at the critical point, at 16 over roots of 3, notice that's where our first derivative, where our slope is 0, where our slope is 0, are we concave down or are we concave up? So I'm just going to do it that way. If we take our second derivative, A is still a constant out front, a positive constant because our strength is a positive value. If we take the second derivative here, the derivative of 256 is 0. The derivative of minus 3W squared is minus 6W. If we substitute, if K is positive, if we substitute this positive number in for W, 16 over root 3, we're going to have a positive K times negative 6 times positive 16 over root 3. So positive times positive, we're going to get a positive for our second derivative. I'm sorry, a negative for our second derivative. Positive times positive is negative. That means we are concave down. So since 16 roots of 3 is our critical point, and at that critical point we're concave down, then indeed that is a maximum. That is where our maximum occurs. They ask, what are the dimensions of our beam? So our maximum width, or the width of our board that has the maximum strength, that's W. And then we can use this equation here to get the height. The height squared is 256 minus W squared. So the height squared is 256 minus 16 over root 3 squared. So 256 minus 16 squared over the square root squared. Our common denominator will be 3. So 3 on bottom. On top, we would have 256 times 3. So 768 minus 256. What do we do there? We just rewrote 256 with a common denominator of 3. So multiply top and bottom by 3. So 768 over 3 for the first fraction, 256 over 3. So 768 minus 256 is 512. So our height squared is 512 over 3. Take the square root of both sides, so that would give us our height, square root of 512. So that's not a perfect square. So whatever we get for the square root of 512 over 3, that would be our height. The width, what was our width? It was 16 over root 3. Now, of course, if you say, okay, here's your log, cut it that size, I'm going to be like, do what now? So what is that related to? So 16 divided by the square root of 3 is about 9.24. And our distance, our lengths were in inches. Our height, how tall is it going to be? 512 over 3. Take the square root of that, so about 13.06. So to the nearest hundredth, these are the dimensions of that beam that we could cut out of a log that has a diameter of 16 inches. And this would be the strongest possible beam that we could get.